YouTube channel. Okay, so we left off looking at some practice problems back here. So where was it? It was question B on 18.26. So we're going to start with benzene, and we're going to try to make, what would this be, paranitrochlorobenzene. So I'm going to have to switch over to a blank document to solve this because I was running out of space. On that one, I don't have a lot of space here either, but we'll give it a shot. So let's see here. We had, we were starting with benzene, and we want to make, and of course this is 18.26b. We want to make this compound where we have a nitro group and a chlorine installed on it. So what are we going to install first? Anybody have an idea here? Would you put in the nitro group first or the chlorine first? And it's not a trick question. Yeah, right. Thanks, Maria. You put in the nitro, right? Because the nitro is a meta director. Exactly. Right. And the chlorine is an ortho pair director. So we want to put that nitro group in first. So we're going to do nitric acid mixed with sulfuric acid. You want to make sure you wear your old clothes and you do that reaction. And that gives you nitrobenzene. And then to add the chlorine group, we just do a standard chlorination. I'm going to use chlorine and aluminum chloride, and there you go. That's it. That's it. That's all, as we say in French. All right, we're going to save C for Monday. So we're going to save 18.26C for Monday. And now let's do 18.28A. So let's see here. Do I have enough for here? Yeah, here we go. So we'll do 18.28A. So this is 18.28A, and we're starting with benzene. Again, I like these kind of problems. They really challenge you. You know, you have to know your reactions quite well. So we have an isopropyl group, we have a bromine, and then we have an acetyl group here. So let's go over these. The isopropyl group is an ortho para director. This is an ortho para director. And then here we have a meta director. Okay. And so our meta director is a moderate deactivator. And if we go back to our ortho para directors, well, the bromine is a weak deactivator. So weak deactivator. And the isopropyl group, that would be a weak activator. So weak activator. All right. So the question is, you know, which one of these things do we want to install first? Does anybody have an idea of which one of these you would want to install first? Because there's a very specific order that will work here, right? See, on the alkylation, right? We want to put in the isopropyl group first. The problem with putting the carbonyl in first, right, is that the carbonyl, if you were to put the carbonyl in first, right, then you'd have a deactivator, and you want to get the highest possible yield. And so if you put this one in first, it's an activator, right? And so that would give you a better yield if you put in the alkyl group first. So let's try putting in the alkyl group first. So we're gonna use we're gonna use, come on, isopropyl chloride, and we'll use aluminum chloride, and that's going to install the isopropyl group, comme ça, as we say in French. Okay, and then since this is going to direct to the ortho into the para positions, we're going to want to put the moderate deactivator in first second, because if we put that in, then both groups would direct to this position. So we're going to do our Friedel-Crafts acylation. So we're going to use this compound. So this would be the analogous acyl halide. So we're going to use aluminum chloride as our Lewis acid. And that's going to, it's not very pretty. It's kind of an ugly ring, but whatever. We'll move on. And then to install the bromine, right? Both of these are going to direct to this position. And so we're just going to use bromine. We're going to use bromine and iron-free bromide, or you could use bromine and aluminum bromide. Either way, doesn't matter. Let's pick aluminum bromide just for a change. And there you go. So we're going to come back, like I said, and solve those other synthesis problems next class. So if you did the reverse, would you need the blocking group with the reverse? So do you mean installing the acyl group first? If you put in the bromine won't, yeah, you would have to use a blocking group. So that would take an extra step, right? And then when you have the isopropyl in the bromine, yeah, I guess it would direct to the para position, but not as well, because if you make this molecule, the good thing about this molecule here is that both groups direct to the correct position. So that would be the best synthesis, right? Less steps. Great question. All right, let's move on from there, and let's go back to we're towards the end of the chapter now. Just bear with me here and I'll find it. Was it somewhere around here? Okay, so now we're into section 18.13. So now we're getting out of electrophilic aromatic substitution. In fact, on the last slide, you could write electrophilic aromatic substitution, done. Okay, we've completed all of that, and now that was the vast majority of the chapter, and now we're on to something new. Nucleophilic aromatic substitution, you know how we learned SN1 and SN2? We call this an SNAR reaction. So SNAR. There's all kinds of other SN reactions that we don't look at, but an SNAR reaction. So check this out. Kind of a new concept for us here. It says an SNAR reaction, okay, which again is just a nucleophilic aromatic substitution reaction, is a reaction where a benzene is attacked by a nucleophile. So you can see here in this reaction that somehow you're taking para-nitrobromobenzene, treating it with hydroxide, and hydroxide is actually behaving as a nucleophile here, and we're kicking out the bromine somehow. So this is like an SN2, but it's on an sp2 hybridized carbon on an aromatic ring, so we call it an SNAR. So a hydroxide is our nucleophile, and the bromide acts as our leaving group. So how does all this work? Okay, well, first of all, there's 3 requirements that have to be met in order for an SNAR reaction to occur. I've seen this tested on MCAT and ACS, so I'm just going to write that down here because I always have some students who are interested in these kinds of things. Okay, I've seen this tested multiple times in those review materials. So it says, first of all, the benzene ring has to possess a strong electron withdrawing group. So look, if we go back here, we have a strong electron withdrawing group. So criterion 1 met. Number 2, the ring must possess a good leaving group. Well, looky. You have a bromide, good leaving group. So the second criteria is met. What's the third one? The third one is the leaving group has to be either ortho or para to the electron withdrawing group. So if we go back here, the electron withdrawing group is the nitro, and so these are the ortho positions, these are the para positions, and so the bromine happens to be in the para position. Good. So everything is set, the stage is set for our SNAR reaction to work. So you have to remember those 3 criteria that must be met in order for an SNAR reaction to occur. And believe me, they will come up on the quiz, and they will come up on standardized exams. So let's take a look. If you try the same kind of thing with your electron withdrawing group at the meta position, nothing happens. Okay, it doesn't work. And so what that tells you is that the mechanism is not simply a nucleophilic attack followed by loss of leaving group. It must be more complex than that. All right. And the reason why is because it goes through something called a Meisenheimer complex intermediate when the nucleophilic attack occurs at the on the bromine when you have the electron withdrawing group at the ortho or para position. So at the bottom it says, with the electron withdrawing group in the meta position, it is unable to stabilize the Meisenheimer complex intermediate. So you have to know what the Meisenheimer complex is. Are you ready? Here we go. Kind of an interesting mechanism here. So when you get the nucleophilic attack occurring, okay, you do not have an arrow that looks like this. It doesn't just cause the leaving group to leave. What it does is it causes the pair of electrons in this pi bond to go into the ring, and then they can be delocalized, right? We move them down to this carbon. There they are right here. And we can actually draw a resonance structure, another one where they're on the ring, but we can even draw one where that second negative charge is, where is it? Right here. We can draw a resonance structure where both of the negative charges are on the oxygens of the nitro group. Look at all three of them. So this is the Meisenheimer complex here, all these four resonance structures. Look at the difference. In the first three, you have a negative charge on one of the oxygens, but in the last one, the negative charge is on both oxygens. All right. And so if the attack occurs at a position that is meta to the nitro group, to the electron withdrawing group, you don't get that. Okay. And so then once you have the negative charge on both of the oxygens of the nitro, in this case, it expels the chlorine. So you can see it's not just a simple loss of leaving group one arrow. It's actually a collection of what? 1, 2, 3, 4 arrows that have to be drawn in order for the chlorine to be expelled. So there you go. So there's your Meisenheimer complex and your loss of leaving group. So you might have noticed that with the sodium hydroxide that there was a second step, which was using aqueous acid. So if we go back here, if you're like, what the hell are you talking about? What I mean is this. The first step is sodium hydroxide, but the second step is H3O plus. What's that for? Well, the reason why you need that is you're doing the reaction in a strong base. So once you get to this point, that proton on the phenol is going to get deprotonated by the base. And so you need to add an acid in to reprotonate it. All right, that's what that's for. And I'll show you that right here. So again, once you make the phenol, it gets deprotonated to make the phenoxide. So you call this a phenoxide. And then you do a proton transfer. So of course you take your H3O plus, so you throw acid in at the end of the reaction, right? And that's just going to do a proton transfer like this and regenerate your phenol. So it's a two-step process, right? A two-step process that occurs here. So with that in mind, it says predict the product of the following reaction. So we're taking this compound here. We have a strong electron withdrawing group. And then we have two good leaving groups. A bromine is a good leaving group and a chlorine is a good leaving group. Okay. Then we have sodium methoxide. So that's sodium plus and methoxide, right? Minus. So this is a good nucleophile. My question to you is, where is the nucleophilic attack going to occur? On the bromine or the chlorine? It's only going to occur on one of them. It's going to occur on the chlorine, isn't it? Right? Because the bromine is meta to nitro. And so that's not going to react. But the chlorine is para or ortho, but it's para to nitro. And so it is going to react. All right. There you go. So we're going to get our nucleophilic attack, loss of leaving group, and of course it's going to proceed through the Meisenheimer complex. And so we end up with our nitro group and our bromine untouched, and then we install our methoxy group. So there you go, a new way to make an ether. All right. So to rehash, what do you need? You need a strong electron withdrawing group. Okay. You need a good leaving group. It's usually a chlorine or a bromine. And then number 3, we'll put here leaving group is ortho or para to electron withdrawing group, right? Those are the 3 criterion that must be met for an SNAR reaction. All right, let's see if we can apply our SNAR chemistry to a problem here. It says, starting with benzene and any other necessary reagents of your choice, design a synthesis of the following compound. Wow, okay, so let's see here. How would we use SNAR chemistry to make this compound? Well, what I'm thinking is if we have an NH2 group, right, that would come from a nitro, because that's the only way we know how to install an amino group. So if we had this, right, we have NO2 like that, okay. And then, okay, let's figure this out here. So then if you had a good leaving group, right, because hydroxide is not a good leaving group, so you'd need something where you have a good leaving group, para, so maybe a chlorine is what we'll pick, right? So then the question becomes, well, how would you make this molecule, right? What would you install first? If you want to make this molecule in blue, would you put in the nitro group first or the chlorine first? And it's not a trick question. Anybody have an answer on this one? Would I want to put in the chlorine first or the nitro group first? Right, I'd put in the chlorine first, right? Because the chlorine, right, the chlorine is an ortho para director, and it's going to direct at the para position, right? Because the only time we assume the ortho is when it's toluene, right? But the nitro is a meta director, right? And so that would direct to these positions, right? Whereas the chlorine is going to direct to this position. So we'll put the chlorine in first. So now we have a start to our synthesis. So let's take benzene and let's turn it into chlorobenzene. So we're going to treat it with Cl2, AlCl3, and that's going to make chlorobenzene. There we go. And now we can do our nitration. So we're going to treat it with nitric acid and sulfuric acid. And that's going to install our nitro group. So let's pencil the nitro group in here. Looks good. All right, now we need to do our SNAR chemistry. So we're going to install the hydroxyl group. So what were the conditions? Step 1 was sodium hydroxide at a moderate temperature of 70 degrees Celsius, but of course that makes the phenoxide. So you have to protonate it. Yes, using H3O plus, good. And so that's going to give us the para-nitrophenol. So here we go with that. So we have para-nitrophenol. And then the last step is to reduce the nitro down to the amine, all right? And so we're going to treat that. That's going to be a two-step process. Step 1 is going to be iron or zinc and HCl, and you can heat that. And then if you want, and then step 2 is just going to be sodium hydroxide to deprotonate the aniline, and that is going to give you the final product. So again, if you like puzzles, that's kind of what this chapter is like, right? You got to memorize all the reactions and then know how to use them to solve a puzzle like this one. Okay, so that covers SNAR chemistry. So again, this reaction here, this is our SNAR reaction, and that brings us to the very last section of new chemistry, which is elimination addition. And you're going to see something really wacky in this section. Check this out. I'll just whet your appetite with this. So everybody knows, who could name this molecule that I'm drawing here? What's the name of this molecule? Anybody? Yeah, benzene, right? Okay. So what happens when you put a triple bond in it? So if you put a triple bond in it, then you call it benzyne. Okay, so you're going to see the benzyne molecule. And if you're like, what the hell is a benzyne and how could that even exist? I thought that these two carbons are sp hybridized. And I thought they had a linear molecular geometry and you have them in a ring. Oh, good grief, this class, you know. Well, I'll explain it a little bit more here. So we're going to talk about benzyne. And believe me, I'm not an expert in benzyne chemistry. There is somebody at UCCS, though, in our chemistry department who is, as a matter of fact, an expert in benzyne chemistry. So anyhow, the SNAR reaction, let's see, doesn't occur if the ring doesn't have a strong electron withdrawing group. Okay, so you try to do an SNAR on this guy, nothing happens. But you know what, Maria? Chemists love to test the limits, right? They just, well, what if I heat it harder and higher? You know, like what's going to happen then? So check this out. Somebody, and I don't remember who it was. I don't even have it written in my notes. If it was somebody in the company or something got the idea, they said, well, I'll just heat it up to 350 degrees Celsius. And then it did react, okay? So you take sodium hydroxide, treat it with chlorobenzene, and you crank it up high. I mean, 350, that's ridiculous. So it's really high temperature, but they went from chlorobenzene and they made phenol. And the question is, like, what's the mechanism? It's not an SNAR because SNARs only need 70 degrees Celsius. And so how did this even happen? You know, how, like, the WTF kind of thing. Okay. And check this out. It says the reaction works even better and doesn't require high temperature if you use a stronger base. Okay. So remember the amide ion. So this is Na plus, right? NH2, right? Minus. So this is an even stronger reagent, okay, the amide ion. And so they tried that at room temperature, I guess, and got it to work. And again, it's not an SNAR reaction, can't be, because there's no electron withdrawing group. So what's the mechanism here? It says the regiochemical outcome below means that this reaction doesn't proceed through an SNAR. So look, to prove it even further that it wasn't an SNAR, they came up with this clever idea. They said, well, let's take parachlorotoluene, this molecule, and let's try these conditions. And they got a pair of regioisomers, right? They got para methyl aniline, and then they got meta methyl aniline. So they got two products. And so that means it's not, so SNAR, it is definitely not an SNAR reaction. So again, we're trying to set the stage for like, what kind of reaction is this? Okay. How does this even happen? And it occurs by a mechanism that we call elimination and then addition. So check it out. Somebody even thought up an idea of doing an isotopically labeled experiment. So what they did is they put carbon 14 in the molecule. So where you see the little star, this is carbon 14, okay? And then they tried the same reaction and they saw that the carbon 14 was in these two positions, right? One attached to the nitrogen and one next door. And so the only way that they could rationalize this was that it must have proceeded through this benzyne intermediate. So check this out. The first step here, this is an elimination, right? Elimination, right? First, you're removing a proton in the first step, and then you lose a chlorine in the second step. So you're losing a hydrogen, then a chlorine, and you form benzyne. Now, again, if you're looking at that and going, oh, that's impossible. How could that even exist? Well, I'll talk to you about it a little bit more in a second. But imagine you did have this molecule, benzyne. Well, you can imagine that if you did have a triple bond in a ring, that wouldn't be very stable. And that thing would be so excited to react that as soon as you put any kind of nucleophile around it, it's going to go crazy, right? Benzyne hurts my eyes. Right? Okay. So look, Jaylin, let's get rid of it then. If you put it in the presence of a nucleophile, right? Amide is not only a base, but it's a nucleophile. It would do a nucleophilic attack to give you this carbanion here, but right, it could attack at this carbon or it could attack at this carbon. It can, I wanted to use the green highlighter, green. It could attack at either one of the carbons in the triple bond. And so that is why the radio-labeled carbon ended up in those two different spots, all right? So we call it elimination, right? This part was the elimination. That's elimination. And then the second part here, this part here, this is the addition, right? And the addition could occur on either carbon of the triple bond, right? And so that's why we end up with these two quote unquote regioisomers here with the radio labeled carbon in it. So there you go. Elimination addition. Now I don't even know if I put anything in my notes. Let me just check here. I didn't. I did not put anything in my notes about the structure. I'll talk about it in a second. Just give me a second here. So here's the mechanism of elimination addition. You know that reaction with the chlorobenzene, right? And they took it and they heated it up to 350 degrees Celsius. Okay, 350 degrees, whatever. Okay. And then they did the chemistry there. Well, you know, this is the reaction mechanism. Okay. First step is just a proton transfer. You form this carbanion, and then you have your loss of leaving group, and you make your benzyne molecule. So there's your benzyne, and now your nucleophile could attack at either carbon, and then a proton transfer in the end. I've never asked this mechanism on a quiz ever in my life, and I don't see myself doing it now, so don't really stress about it that much. But there you go. So you get a proton transfer in the end, and that's all she wrote, kind of thing. So elimination addition proceeds through a benzyne. And, you know, if you're wondering, well, you know, I don't believe it. I don't think that benzyne could actually exist. There is some proof of it. So what they did is somebody, when they did an elimination addition reaction, they threw furan, which is a diene, in the reaction mixture, and benzyne would react as a dienophile, right? And it made this whole cycloadduct here, okay? And so they actually proved that benzyne does exist. But if you look in our textbook, so I'm not going to lecture on this because it's not pertinent to us. You're never going to be tested on it or anything. But they said how the benzyne and you'd have to look at it yourself, but some people say the benzyne is kind of like, it's like almost like it's a diradical like this, right? Like it's a diradical like that, and then they kind of partially overlap. Somebody says if there was no nucleophilic attack on the benzyne, would it just pop open? No, because you have to have a strong base in there, and so the base can always behave as a nucleophile. Does that make sense? Right. In order to do the reaction, you've got to have the strong base in there. Yeah. Yeah. Good question. Yeah. Great question. Anyhow, I'm never going to ask you about this, not in 100 years. It's just more of an FYI. And I know you're inundated with enough information at this point that you don't need me to start lecturing on new things, you know, that you don't need to know. But there you go. So that's elimination addition. And with that in mind, let's try one practice problem with respect to elimination addition. It said draw both products that are obtained when 4-chloro-2-methyltoluene is treated with sodium amide by treatment with followed by treatment with aqueous acid. So we've got 4-chloro-2-methyltoluene. So that would be, if we draw a toluene, it looks like this. If we put a chloro here and then a methyl here, so that's 4-chloro-2-methyltoluene. And then we're going to treat it with sodium amide. So that's Na plus, NH2. No, I get ammonia on the brain. There we go. Sodium amide, and of course that's in ammonia. It says draw both products that are going to be formed. Well, let's see here. And of course, the second step is by treatment. So this is step 1. Okay, and then this is going to be step 2. So we're just thinking about step 1 right now. But where are the protons that could be removed in order to eliminate, you know, the chlorine? Well, first you could eliminate this proton, or you could eliminate this proton here, right? You could remove either one of those, and that will give you the desired product. So let's say you ripped off the proton in blue, and I'm not going to draw the mechanism, but let's just imagine we did rip off the proton in blue. Then the benzyne intermediate that you would get would look like this, right? And then what's going to happen is that the amide could come in and it could attack at this carbon, or it could attack at this carbon, either one. And so you'd end up with this. So you'd end up with this guy where you have something that looks like this. And you'd also end up with this. So where the amine is over here, like that. Okay, so you end up with these two guys. All right, and then the other possibility, if you ripped off the proton in red, so I'll just do it like this. Same thing, so Na, NH2, and ammonia. If you ripped off the proton in red, I'm just going to shift the bonds around, okay? Then you'd end up with this. Oops, fix this one here. All right, so you'd end up with your triple bond here, and then you end up with both of these, right? And this can only give you one product, which would be, doesn't matter which one of those carbons it attacks, you would end up with this guy like this. And you probably noticed that these two are identical, right? And so the only products that you would end up with would be the product in the green circle, and then I'll put this product in a black circle. So those are the two products that you would get, and that's it. All right, so a little bit of elimination addition chemistry. And so what did we learn in chapter 18? Oh, a few things. Okay, but the main part of the chapter that went up to until 18.2, I think. No, 18.12, I mean. 18.12, we did EAS, electrophilic aromatic substitution. And then 18.13 is SNAR, and then 18.14 is elimination addition. So the vast majority of the material that we covered was electrophilic aromatic substitution. And so if you have an electrophilic reagent, it's going to be an EAS reaction. If you have a nucleophile, on the other hand, then it's going to either be an SNAR or an elimination addition. All right? And the only way you differentiate between these two is just, you know, are the 3 criteria satisfied, right? And I went over those with you a couple of times. You've got to have a strong electron withdrawing group, good leaving group, and it has to be ortho or para to that strong electron withdrawing group. So there you go. So this one here asks us to draw a mechanism. And of course, this is going to be an elimination addition mechanism here because we're taking this aryl halide and we're heating it up with bromine, heating it up with sodium hydroxide at 350 degrees Celsius. And so we could, do you want to do this mechanism now or do you want to try it and save it for Monday? I'm good either way. I'll give my students who showed up to class a vote. Anybody try it on Monday or do you want to try it now? Somebody says now, let's go for it now. All right, let's try it now. So you ever notice that the first person who answers always wins, There we go. Okay, so let's see. We have our strong base. Okay, so I'll draw my hydroxide ion like this. And that's going to abstract the proton. And we're going to cause the leaving group to leave. And that's going to form our benzyne. So we'll draw our benzyne molecule like this. So now that we've got our benzyne, we're going to have a nucleophilic attack by the hydroxide. It could occur at either carbon. So I mean, it could occur here like this, or it could occur here like this. Either way, you're going to get the exact same thing. So let's just draw, we'll go back to the first ones. Oops, I didn't do it right. So we'll go here and here like this. So that's going to give us this intermediate, which looks like this. There's our carbanion. All right, and then the last step, we just need to protonate it. But remember, we're in a strong base. We're in sodium hydroxide. So that phenol proton is going to be removed by a molecule of, an ion of hydroxide. So we pull that off. We make the phenoxide. So we have our phenoxide. And then this is the last step where we do our proton transfer with hydronium. So we draw our hydronium ion and we get proton transfer, and there you go. So there's the whole mechanism. And again, this is 18.14. This is elimination, addition. All righty. With all that in mind, that brings us to the last, kind of the end of the entire thing. So all the reactions have been covered now. And remember, we went over SNAR, we went over elimination addition. So there's two types of elimination additions. The ones with sodium hydroxide, so let me put here, the ones with NaOH are at 350 degrees Celsius, okay? And I know you can see that. And then the ones with amide, no high temp required. All right, and that's how you kind of remember the difference between the two. Nothing more than that. And that's the entire chapter from soup to nuts. Okay.